Well, good morning. Bill Ragsdale here. We're going to do the part 3 of the Wordle challenges for the SVFIG here at June 25th, 2022. First, a refresher on the Wordle game. The Wordle game took the world by storm starting about last December. On it, online, you guess a 5-letter word. You have 6 tries to guess that word. You get some hints. A correct letter in the correct position will be shown in green, and a correct letter will be shown in gold. We're building tools now to support the Wordle game. Here's an example. The first guess for this puzzle would be the word ridge, and the fact we got 2 gold and a green IDE gives us a start. We then picked the word doggy. We picked up the letter D. That led us to the word diode. It had fewer letters, but we see where I and O are, and the D and E at the end. And finally, the word oxide, and it's all green and it matches. So we're building tools to work on the Wordle game. The challenge today is to develop a list of 5-letter words. 20 or so would start. In this case, I used about 2,000, which is from the Wordle list. The Wordle total maximum list is about 12,000 words, all 5-letter words. From this, we'll form evaluation criteria for the closeness between the words. This is kind of like the letter frequencies for the alphabet. Well, in this case, it's the frequency of usage or compatibility between words. And finally, then, for each word on the list, we'll rank its closeness with the remaining words. Here's the exact list of Wordle words. They have 2 sections. There are about 8,000 words that are eligible to be used, but are unusual or rare words that are not included, and then about 2,300 of the very common English words. This is taken right off of the cache from my computer, and when you're playing the Wordle game, you actually have this list in your computer. Here's an example for the ranking criteria that I developed. Over the N 5-letter words, in this case, N is about 2,300, we selected test word. Then for each letter in that test word, we'll compare it to all of the other words on the list, which is N-1. Every time a letter appears in our test word and the input word, we score 3 if they're in the same position. If the letters appear simultaneously in both words, but not in the same position, I score a 1. So a little example at the bottom left. The unknown word is the word stare, and we're testing against toast. So we see that under the T is a number 1 because T appears 1 time in the unknown word stare. Under the O is a 0 since there's no usage. Under the A is a 3 because A appears in the 3rd position for both words. Under S, again, it's a match. We have an S. And then we come to the final T. Now, T is only used 1 time in stare, and we've already caught it on the first T in the word, so there would be a 0 under the last T. You see, a word can only be scored once. If it appears twice in both words, it'll be scored twice. Now we're to the 4th. Let's look at building the files. First, we have a disk file. It is Wordle daily list.txt, and we see the full path of from the directory. In this case, I'm using Win32 4th version. It's the latest version, and these access words are taken from the ANSI standard 4th. So first, we name the disk file into an array. We open the disk and get its file ID. That is done by the word open file. And it reports to the word my file ID, which holds the FID. Next, we find the file size. That uses the 4th word file size, obviously. And finally, we copy the disk words to a 4th array. So my file contents is the destination. We know my file size. We know its ID. Read file reads it into my file contents. Now we need to count the words and create a matrix of the proper size. So I have a utility word that I developed, count words. It goes into the file contents. It does a scan by letters. count the total number of letters, and then actually it looks for the ASCII comma, and the ASCII comma tells it how many words are in the file. Then in the bottom, we see we create 2,309 times 2 matrix words. This is done in the word set. We actually it's a 2309 by 2 matrix, 2 columns of the matrix, and that word, all the words appear in word set. The next word form matrix pulls all of the words sequentially from our input buffer into that matrix. It's done this by letter. So there's a couple of values that are used to keep track of where we are. And to over my file contents by file size, we do a do loop. One of the key words is the query ASCII, question mark ASCII. This determines if we have a letter in the range between A and Z. If so, it is added into the matrix in the proper position. On the other hand, if it does not, and it is an ASCII J, we then reset because we've now reached a new word. So sequentially, this passes through all 2,309 words, letter by letter. Here's a utility to print out the matrix. Remember, there's 2 columns. The first column is the word. The second column will be the usage. So we have a do loop that simply scans through the matrix. It goes to the first column and does a print word, which prints out the 5-letter word, 3 spaces for formatting. The next line then with a dot, with an F dot, prints out the floating point value on the scoring. And the simple loops across all 2,300 words. Here's an example that we get then from the very, very start. We've taken word set and formed the matrix. We've taken that same word set, and then with the parameter 10, we print the matrix, and it will print the first 10 values. So these are arranged in a random value in the input set. We see the words like cigar, rebut, sissy, hump, awake, and so on. And at the moment, they're all scored as 0. There's the word that does the scoring. Remember, we have 2 situations. If the words are in alignment, we score 3 points. If the letters are not in alignment, but they match in both words, we score 1 point. So there are 2 do loops. The first do loop checks with the 3-point situation. And if that does not occur, it goes down and checks for the 1-point situation. This is extending the scoring now. The prior word only did 1 word at a time. This sets up a double do loop to go over all of the words. And so it scans through the list the first time, picking out the unknown word. The second do loop picks the test word. And if you see on about line number 5, there's a greater less than sign. This assures that a word will not be tested against itself. In red, we see the bracket score negate. Bracket scores the prior word, scores the particular word against all other words, and negate switches the value to its negative value. This is so the sort will go from the greatest to the smallest value. Normally, the sort goes from the smallest to the greatest value. Then down at the bottom, the next to the last word does a conversion to floating point. All of the math above is done on the stack as integer arithmetic, and then finally within the matrix we put down the floating point value. So here's the scoring for 1 word, and we've already seen that. We'll bump ahead. Score all words. All right, after the scoring, here's what we come up with. The word stare has a compatibility score of 5,388. This would be expected. It's the most compatible word with all the rest because S, T, and R are the most common consonants in English, and A and R are the most common vowels. The following words like arose, raise, arise, slate, erase, and so on are all quite similar. Again, they're using these very common vowels, very common consonants. And again, the popular vowels using A, E, or possibly I, or possibly O. If we reverse the sort, we can look now at the low-ranked words. Well, the lowest ranked word in the whole list is fuzzy. It only has a score of 1832 because, again, it's using the letters F, Z, Z, which are very low usage, and the consonants U and Y, which are low. Another one, very low usage, would be humph, for example. There's only one vowel U in the word. The most difficult word I found in using Wordle in real time has been the word fjord, F-J-O-R-D. That one gave me fits. I'm not sure I got it in 6 letters, in 6 tries, if at all. So here's the performance. We've seen how we developed the lists from file. We put them into a matrix. We did a double scan on the matrix, scored all the words, and we listed the priorities, both increasing and decreasing. So how did Forth do in handling this? Over the 2309 words, there was 5.9 million word comparisons made. And within that, during those comparisons, there were 133 million letter comparisons. And this took a total of 24 seconds. This was followed by a 2300 item bubble sort, which meant that 2.7 million floating point comparisons were made. That took 6 seconds. And you can see in this situation, we have 0.45 megaflops execution speed. So there we have it. We've developed the actual Wordle word set. We've found out the best words to use for searching. And we've also gotten a little hint at the kind of words we would not want to search from. So let's look ahead. This is our July challenge. I'm proposing that we take this Wordle support another step further. We develop an alphabetic grid such that when an unknown word is tested against a series of known words, as we were doing today, we actually build a grid for that unknown word. The unknown word is held by in the grid by the letters known in their location. If they're known and the proper location, they're in green. They're marked in one part of the grid, and if the letter is used but unknown, it's marked in another part of the grid. So the grid has 2 sections, the known letters and the letters known by exact position. Our purpose on this is to sequentially improve the grid as a model of the unknown word. As we make 2 or 3 tests, the grid will get closer and closer in alignment to the actual word. And eventually, of course, it will find the proper word where all 6 letters match. On the other hand, though, Wordle only allows us 6 tries. So that means the searching process has to have a little more intelligence about it. And we'll probably work on that intelligence in future challenges. So I'd like to thank you all. Goodbye, good night, good day, whatever time zone you're in. And this is Bill Ragsdale, and we are now back to Kevin, our fearless leader. Thank you.
Can folks hear me?
Yep, I can hear you.
Cool.
I can hear you.
While I'm at it, I made a crack at solving this during the session, and building on some of the stuff from previous times. Nothing too radically different from Bill, minus the matrix library, but pulling in the dictionary, uppercasing everything in the dictionary. I have some iteration words to help me walk through all the words that I've pulled in. I have words to check whether something is a letter and whether it is whether everything is whether a given item in the dictionary is the appropriate size, and then I go and build up a table of the ones that meet that filter for convenience, so that I don't need to repeatedly refilter it. I think I might have found a bug in my micro eForth with this. I was building straight into the dictionary with comma, and something isn't working, but I sidestep that for the moment. So this is a little bigger than I would like, but this may have proved to find a bug. In any event, I have a scoring function, a slightly different than Bill's, but pretty much in the same genre. I count essentially 4 points for an exact match. I count it against you, against a word, or sorry, I count it in as a positive whenever there is a match, regardless of position. And then I sort of ding words for self-matching, so that because they're then expending budget on letters that that you'll get partial information on. So kind of just an arbitrary heuristic. I'm then able to go over all of the words and score them individually, so I can produce a score for a single word, and then I can go and score each of the words. As I was largely doing this during the duration of the meeting, I did not have time to implement a sort. I probably should have a more convenient go-to sort, I'm realizing. So I cheated and used Unix command line utilities to do that sort. I got similar but not identical top words from this list. The score can go negative. This particular heuristic seems to favor words that end in es, likely because it's giving a decent amount of weight to an exact match over a large set of words. Further down, things get a little more interesting. I have not tried these extensively, so I can't speak to whether they're particularly good initial words, but and in the event, that's what I have on that. Cool. Any questions on that, or we can move on to the next segment? Let's do that.
Does anyone else have a solution?
Oh, yes.
All right, Brad, it looks like you have time to do your presentation and then get into the Ting Memorial and maybe run over a little. Are you willing to do that?
Absolutely. Yeah, sounds
The
good.
alternative is to drop your talk, which I would prefer not to do.
Okay. Yeah, I'll try to keep it short and to make sure we've got. If anybody's got time constraints, let us know. I would, especially if you want to say something